Andrew, would you take over?
Say again, sorry.
Yeah, would you take over pasting the link when people
Yes.
come?
Yep, no problem.
Okay. And those participants already here, did you do the homework? Did you go to the dark room?
Yes.
And what happened when you went to the dark room? Absolutely dark room. What happened?
I don't know. It was too dark to see.
Yeah. Okay. Well, if this is what happened, that's great. Yes. So
I thought I was invisible. You know, like I thought I was invisible. I couldn't see myself. I can see me.
Right.
I knew I was moving, but I couldn't see but then after a long time, 15 minutes afterwards, I could start seeing me again in the dark.
No, that's not possible. That is not possible.
No, why is it possible? Because
No.
there was a few places.
No, you just were thinking, no.
There were
If
few
you did
cracks
not have any sources of light, you shouldn't be able. This is
It's just not possible to create absolutely dark room.
Right, right.
So
right.
I saw a few rays of light of a place that I couldn't cover through the top.
Oh, yeah, yeah.
I could see that line, but I couldn't see it at the beginning. It took
Oh, okay, okay. No, if you could see lines of light, then you were not in an absolutely dark room. That's why your eyes adjusted. You need to be in a room where, Chris, I need to see how many people are there. Oh, maybe we will not have so many.
We have 14 right now.
Yeah, right. But this is a lot of organizers here.
Yes.
I think they may be updating. Did you have to update Zoom, Andres?
No, this time I didn't.
Uh-huh.
But regularly, yes, it rarely asks me to update the Zoom.
Okay.
And to your college, people are notoriously late. So
well, if they're late, they will be late because we're gonna start. That's how it will go. Hi, Leon. Yeah, please rename yourself like we all renamed with the first name, where you teach, like university or high school, I mean, university, and then the country, because we have different countries and different institutions where people teach. Do you see the link to the slides?
Yes.
In the chat?
Uh-huh.
Okay, I am going to the slides. So the second slide tells you how to rename yourself, and the third slide has the links to the materials that we will be using. And the fourth slide has the schedule, which is very, very tight. So it is 10 o'clock on my screen, so I don't know what to do.
I'll just do a very quick introduction. So welcome everyone. I'm Chris, and I am Director for Optics with the American Association of Physics Teachers, which is an organization for physics at two-year colleges. And we have a couple of upcoming events. You can get more details on our website, which is linked here through the QR code. But coming up, we have a virtual workshop on energy first approach, and then 2 related sessions dealing with scientific reasoning in labs. And today we have the IEL workshop facilitated by Eugenia and Anna and Andrew. So I will stop sharing and turn it over to you.
Hey, hello everybody. Please turn on your cameras. Rename yourselves as the second slide in the slide deck says. You all have access to the slide deck. If you just joined, Andrew will continuously posting the link. So we will be working with you, and there are three of us. I'm Eugenia Etkina from Rutgers, and then there's Anna Karelina, wave, right? And Andrew Yolleck. Yes, our names and institutions are on the first slide. Andrew, please keep posting. I see people joining. So how we will be working, part of the time you will be your students working on activities, and part of the time you will be teachers reflecting and thinking about it. Unfortunately, right before our workshop, Zoom changed controls over the whiteboard. So when you are working in rooms, you won't be able to use the whiteboard. So all drawing and writing would be on the slide for your team. So you will be assigned to teams like randomly, and then in your team, you will know which number it is, and the slide will say team 1, team 2, team 3. So no whiteboard, unfortunately, today. Is that, this is sad news, but that's what it is. Because you will be renaming yourselves, everybody will know your first name and where you teach and what country you're from. So to rename yourself, there are 3 dots if you click on your name on top on your video, and it says rename. So please rename yourself. So we have your first name, your institution, and the country. Is that okay? Yes? Yes? Okay, great. Then on slide 3, there are links to the documents. I try to organize the slides that you don't need to click on anything during the workshop, but after the workshop, there are papers about the approach and curriculum materials that are ready for you to use. Okay? On slide 4, there's a schedule, and it is like minute by minute. We will be working for 4 hours and hopefully accomplish everything. Okay? And now I want you to turn to slide 5. Is everybody on slide 5? Yes? Yes?
Yes.
Nod? Yes?
Yes.
Okay, great, great. So these are students learning physics through the aisle approach. I want you to unmute yourself and say, what is it that you are seeing on those pictures? These are high school students. So those of you who teach in high schools will see your kind of students there. What do you see?
Student interaction.
Student interaction, what else?
Data
Come on.
collection,
Right, what else?
multiple representations of what it is they're learning about.
Yes, what else?
Experimentation.
Yes, what else?
No teacher present.
No teacher present. Yeah, great. And do you see the whiteboards, communal whiteboards?
Yep.
On which they're writing. Yes, so this is a typical high school classroom. Now let's scroll down to slide 6. This is a college classroom. Do you see any difference?
Maybe a larger learning environment.
Yeah, maybe a bigger room and all the students, but the foundation is the same. It is teamwork, it is sharing, it is whiteboards, it is a community, right? People are leaning towards each other, and when they lean towards each other, it means they're working together. When they lean backwards, how our research indicates they're not interacting much. So look at those students tilting to leaning towards each other and working together. So this is how the aisle environment works in high school or college. It works best in a studio classroom, but if you have a large enrollment course, then in your recitations and labs, you can create this environment. And if you have a lecture hall with 200 students, they can still turn to their partner and still replicate the spirit of teamwork. Okay. And now I want you to move to, so this is like the visual image. I want you to have an image of what it is. Does it help create an image? Good. Okay. So let's go to slide 7. And I want you to pin me. So you just look at me. I'm very important, right? You see the sweater that I'm wearing? What do you see about it?
Blue.
Don't be
half
shy.
turtleneck. Blue half turtleneck, so not the whole way, but some
Yeah,
turtleneck.
blue. It's blue, right? So that is what you observed. And you understand that you could only say that it's blue because you have a special detector that is sensitive to colors, right? If you were colorblind, or if you were, sorry, like a dog who they don't see colors at all, you would not know that my sweater is blue, correct? So this is an observational experiment. You did not expect me to wear blue today, right? I did not ask you to predict, what color sweater am I going to wear today? And is that, how would I know, right? You did not make any predictions. You happened to notice that I am wearing a blue sweater. So this is kind of an accidental observation, but I, as a teacher, chose a particular sweater. It doesn't have any pattern and doesn't have multiple colors. It's an easy observation. Is that clear?
Yeah.
Yes? Okay.
Yeah.
So now the question is, what is the question? Why? Yeah, why would I wear a blue sweater today? So give me a few wild ideas of why I would wear a blue sweater.
It's your
It's
favorite
comfortable.
color.
It's my favorite color, right? That's what students say first. What else?
It's
It was
comfortable.
the first thing you grabbed from the closet. or
Yes, the first thing I grabbed. What
Random
else?
chance.
Random chance. Yes, could be anything. Okay.
National Blue Sweater Day.
Yeah, National Blue Sweater Day. Great. What else?
You wash your blue socks with everything else.
So I have matching, wear everything blue, right? Students also said that this is the last sweater you have left. Everything else is dirty.
I like that it goes well with the red couch behind you.
Right. Okay. So now we have this multiple hypotheses explaining why I'm wearing the blue sweater, right? So what do we do about them?
Some
How do we decide
investigations.
which one is good and which one is not so good?
Try to rule them out.
You have to rule them out, right? So how do you rule them out?
Asking questions.
Ask me question. Go ahead, ask.
What's your color selection look like in your closet? Do you have an order that if you've worn a sweater, you put it back, and if you haven't worn one, it's on one end, and after
Imam
you wear it-
razlike barve.
What's that?
Imam razlike barve. Različne barve.
What's your
Can I
favorite
check
color?
in your closet? Can I check in your closet?
Yes. So if you ask me, and I answered you in Slovenian, in my broken Slovenian, right? So you could not understand. I answered your question. I actually said that I have clothes of different colors. But you could not understand because you did not expect me to speak Slovenian, right? So you did not have a detector to interpret it, right? And that is a very important difference between the first experiment that we did, that you all noticed that I'm wearing a blue color sweater, and the second experiment, when you you ran an experiment, you asked me, right? You used, sound and stuff, but you could not interpret what I said because you did not expect it, right? And so the expectation is really important. If you do not expect an outcome, you do not have an instrument to detect it. That's why these ruling out experiments that we call testing experiments are very different. Not only that you need to design an experiment, but you need to design an experiment whose outcome you can predict using the idea that you're trying to test the rule out, right? So let's say we are going to test the idea that blue is my favorite color. What experiment can we design whose outcome we can predict using this idea?
offer you different colored clothes and see which one you choose.
So if your idea is correct, right, that blue is my favorite color, then what should happen as the outcome of the experiment?
You should pick blue.
I should choose blue, all blue colors, right?
Yes.
Right. So what if your idea is that I have no more clean clothes, and that's why I'm wearing this sweater, and the color is not important? What experiment you would run?
Get your sweater dirty and see what you do.
Say it again.
Get your sweater dirty and see what you do.
What is your prediction based on the idea?
That you will have to change your sweater, and the next sweater you pick, will it be blue or not blue?
Or not blue, right? So if the idea that this is my last sweater, right? Then if we get it dirty, I should have no sweaters at all, right? Then you look into my closet and you will find no sweaters. So this is a very different prediction compared to the prediction for the giving me different blue colors. But let's say you go into my closet, you dirty my blue sweater, you go into my closet and you do not find any blue colors, any other clothes. Does it prove that I am wearing blue because I have no more clean clothes? Or could I still be wearing because it is my favorite color and I saved it for the last sweater? It could be, right?
Both options are valid.
Right. But if you go and look into my closet and you find no clean clothes, right, at all. Wait a minute. Yes. And you find no clean clothes, then
You fail to reject it.
yeah, you need to reject the hypothesis, right? And so rejection is much easier. So you
No, if you find some clean clothes, then you reject
right.
it. Yeah.
If you find so if you go into my closet and you find some other clothes, you reject the hypothesis that I am wearing this sweater because I didn't have any clothes, right? So the rejection is much easier than proving. And this is basically the process that we will be going through. Asking students to observe, come up with ideas, and then test them for rejection. Okay? And to do that, I am asking you to go to slide 8 and to play the video. On slide 8, can everybody play the video? Everybody has access to the slides, right? Yes?
Yep.
I want Dean, Ali, Larry, AJ, Hanika, Michelle, please turn on your video cameras if you can. Are you watching?
Yes.
Is that a heart?
On slide 8?
Yeah, the video, look, there's a candle. It looks like
There's a candle. Yes,
projector.
yes, the candle.
Is that
Yes.
a project? Looks like a heart though, which is not what I expected.
Okay.
Maybe
So
I'm thinking
you
of
see the
Valentine's Day.
candle? You see the candle?
Mm-hmm.
What else do you see? You see the board with a hole in it?
Yeah, look, that's what I'm saying. That looks like, I guess it's just a slit, but for some reason, maybe I'm thinking of next week. It looks like a heart being projected, not just a slit. Oh, it's the shape of
It's just a
the
little hole
flame.
there. There's no slit. It's a hole. Do you see
Yeah,
the
the
hole?
hole. Yeah.
Right.
It
You see
does
the
look
hole?
like a heart.
What do you see on the screen?
I was saying a heart, but I don't think you like that answer.
A
So I'm gonna
small black
stop now.
dot.
Like the flame upside down.
It's
You
the
can
inverted
see
image
that there
of
is the flame upside down. If somebody doesn't say it, you can't, you will see the heart, you will see the dot, but you don't, but now one of the students say, that's the flame upside down. Say, yeah. So how is it possible that having a little hole in the screen will create the flame image upside down. So this is, now you have been students so far. That is the beginning of our exploration. And what we just did is called creating the need to know. This is a cool experiment, a question, some experience that students had that motivates their interest, but is not explained by the teacher or them at this moment at all. We just say, okay, remember this experiment? By the end of the unit, you will be able to explain why the candle was upside down on the screen, okay? And now we are going to the next slide, slide 9. Try not to delete the slides, please. So whatever you do, do not touch the delete button on your computer. Okay, slide 9. And this is your homework. So tell me, did you go to the absolutely dark room? If you could see any light, it's not good. And who went to an absolutely dark room? Raise your hands. Okay, so what happened when you went to an absolutely dark room?
I could see nothing.
Nothing. Yes, the answer is one word, nothing. Nothing happened. Right? There's nothing to see. It is actually an amazing experience that people who are not physicists never have. Because in our lives, it is impossible to be in a room that has absolutely no sources of light. So you either create this room for your students in your school, college, whatever, or ask them to do at home experiment. And the best thing if you are a high school teacher or a 2-year college teacher is to blacken the room together with them, to cover the windows. And this excitement of not leaving any slits, any sources of light, you know, is a preparation for them. What does it mean to have no sources of light? Okay, so you all had this experience. No sources of light, see nothing. Doesn't matter how long you stay there. And notice, I did not ask you, and I will never ask my students to predict what will happen if they go to an absolutely dark room. Because all of them will say that eventually we'll be able to see something, because they're not wrong. They're absolutely right. It's just they have never had this experience. So remember again, I did not ask you to predict what kind of sweater, what color sweater I'm going to wear. And I did not ask you to predict what you would see if you go into an absolutely dark room. Remember that is really important for our approach. No predictions before students have their first experience. Okay? Okay, so now that we have this experience,
Eugenia,
and I tried to...
What if they give a different answer? So for example, like when I did it, I saw like a sort of kind of some gray, like some difference in blackness.
Right. So what you see at first is the reaction of your eyes and your brain interpretation. You see some spots and then they disappear. That's what everybody sees. So they will eventually agree. That's why creating this dark experience in your classroom is better. Okay, so I created this experience for you on slide 10. That's what you would see. Everybody's on slide 10. That's your dark room. Okay, that's what we do in our workshops. We darken the room, but you know, here I can just do a slide. Okay, so the question is, what did we learn from this experience of being in an absolutely dark room?
That your brain is trying to process what you are experiencing. You know, your brain is trying to make sense of it. Your brain is trying to come up with that explanation. So, you know, like I'm thinking like, oh, there's got to be some radiation happening in this room that my eyes can't detect, but it's there. I just can't see it yet. Like these electromagnetic receptors aren't.
Oh
that
man,
great.
Stop it, Carl. Stop, please, darling.
Sorry. I'll cut myself.
That is exactly what our students are thinking about electromagnetic detectors.
No, I was kind
In my class, they are.
Yeah. That's good. But okay, I forgot to say you're students now, right? So what do you think as students who have this first experience for the first time? So you think no light, you cannot see anything. So for us to see something, we need a source of light, right? So that should be the summary of our first experience, what we call time for telling. Everybody needs to agree on this before we move on. So there's a first observation, and then we need to agree, no matter what topic we're observing, we need to agree what we saw and how we interpret it, okay? We cannot move past it. So everybody needs to agree, no light sources, we can't see anything. But do we see light? Like, what does light do? How does it help us see? So in order to answer this question, students proceed to the next experiment. And what I would like you to do, we are on slide 13, right? And this is the activity in the online active learning guide with the video. But if you have the equipment that I asked you to have, then you use the equipment to run the experiment and answer the questions in your teams. I'm going to put you now in four rooms, right? In your room, read the question. The room will have the number that you are in, as I said at the beginning, and try to answer these questions, either doing the experiment yourself or watching the video there if you did not bring the equipment, if you don't have a laser pointer and a spray bottle. Is that okay? Clear? Your students now? I'm going to create 4 breakout rooms. Andrew, you on 1, Anna, you on 2, and I will take 3 and 4, okay? I'm opening all the rooms. The timing is there. You see the timing?
Eugenia, it says that it's inviting me to room 4.
Yeah, okay.
Do you want me
Then
to
you
go to
take
4
room
instead?
4. Yeah, take
Okay.
room 4. Anna, what room are you in? Oh, okay, I'll see her. Andrew, you go to room 4.
Okay,
Anna
very
is
good.
room 1. Anna, join room 1 and your room will be room 1. Okay, and I will do 2 and 3.
Hey, Tom, I think Joe was also trying to take attendance. But if he's in a room, then I guess it makes more sense for you to take attendance. Oh, you're muted.
Okay. John, what room were you in?
I was in room 3.
Oh, okay. These are people who answered all the questions. Good work.
Thanks.
Okay. Now, I'm just waiting for people to come. I want you to look at the answers from other teams. Okay, great to have everyone back. So of course you all knew what will happen as teachers, but as students, it is based on our experience, it's a very exciting experiment when they can actually see light that they could not see before. And that's what Kanika in room 2, before they sprayed water, she said, it moves in a straight line. And then somebody said, how do you know? Oh, because I see the dot on the wall and it looks like it's along a straight line, right? And then spraying actually reveals the whole path. So how did we answer those questions? I want you to go to slide 19. And see if you agree with their answers. I'm not asking to present because it takes time. Especially part D. Something has to block it and then light comes back to us. You know, in my many years of doing this activity, I never had people say this amazing thing, that it actually, all the objects around us are actually blocking light and reflected back to us. So the word block is a very important thing. And so that is what all these droplets do, right? If there's nothing blocking light, we're not going to see it. And this is exactly what you needed to learn from this activity. And this, again, what did we learn and what is missing is on slide 22. So this is, again, time for telling. So did we all learn that the laser beam travels in a straight line? Yes? Yes. We all learned it because we saw it and we interpreted it, right? How that this line was visible. Second is that we can model this beam that was relatively narrow, right, as just one line called a ray. And this is another model that we're meeting. Remember, we already learned the models of a point-like object, of ideal gas, frictionless surfaces. So this is another model, right? It's not real. It is what we use this model to study phenomena involving light. So we are going to now represent light traveling from a source to somewhere with these rays, okay? And the last thing is that we do not see light, but we see object that it bounces off. I wish because I wrote it before, but I should have said that it blocks, right? That block, we see the object that block light and light bounces back to our eyes. So now we extended our understanding, not only that we need a source of light, but we also need something for it to bounce off and come back to our eyes, right? And so that is the understanding we all want to be at as a class, as a community. But the next question is, you know, laser pointer is a very special device, right? We don't usually use them unless for specific purposes. We use, you know, light bulbs. So what happens when we turn on a light bulb? And if you have that light bulb that you prepared and you're in a dark room, I want you to turn it on now. And I know Roberta has one and Kanika has one, but it would be good if you turned it on. Can you turn it on so we can see and move away? Yes. So great. So what do you see when you turn on the light bulb? What do you see around you? Andrew, thank you.
Light.
Yeah, you don't see light, you see the walls illuminated, right?
Oh yeah.
Remember, you don't see
filament.
light.
So I see filament. Yeah.
Yes, that's why you need a frosted bulb.
Oh, okay.
Right? Do not use the bulbs with filaments. I don't even know where you got the filaments unless it's an LED with something inside. It
Hurts
has
to
to be
look at.
frosted. But look at Andrew, right? Pin Andrew, and you will see that everything around him is illuminated. The same with Roberta and Michelle. Yes, thank you. Unpin. Now remove spotlight. Okay. Okay. So now the next question is, how does light from that light bulb, thank you, Michelle, that's great. How does light from this light bulb reach the wall? How does it travel? Remember, we already created a model of array. So now we need to apply this model to explain how this bulb illuminates everything. I'm going to put you in the rooms again for about 5 minutes. And remember, we do not have whiteboard availability now, you know, silly Zoom. So I want you to draw using the tools in the slideshow, and they have the arrow tools. Just draw them using the tools that you have right on your slide, okay? 1, 2, 3, 4, you'll be in the same rooms, 5 minutes, maybe even less, depending on how you draw.
We had some rich discussion right at the end there. We need more time.
I know. You know why I interrupted you? Because you started drawing too sophisticated models, and I wanted a team that had the model that all students draw to remain before they changed it. It's your fault.
Mine.
Yes. So let's look at slide 27. That is what all students draw. Right? And why do they draw it this way? Why do you think all students, everybody would draw this, no matter what age, adults, it doesn't matter. Why do you think everybody would draw a model on slide 27?
That's kind of the way that it always appears, you know, the sun in the sky, and it's got the radiations coming out of it.
Right. So we asked students, little children, you know, I have lots of grandchildren, to draw, you know, the sun. And they all drew it with, you know, each point radiating one ray. And so this is great, actually. It's an amazing opportunity to teach students to test their ideas, right? So let's say that this is the model that your students come up with. How would you test it? And we see here on slide 26, a testing experiment, right? You block, you put some obstacle, right? So if this model is correct, then what should happen when you put this obstacle?
We should see the shape of the obstacle on the wall.
Sharp shape. And then if you move this, and this is where I would help them, if you move it closer or farther away, what should happen to the sharpness of the shadow?
It should change.
Stay the same.
It should stay the same. The sharpness should not change because these are the same rays that you're blocking, right? So this is one experiment that students come up with, but they also all come up with a different experiment. And that's why I asked you to get aluminum foil. Yes. We put aluminum foil on the desks on the tables, and they all come up with this experiment. Cover the bulb with aluminum foil, poke a hole. And if this model is correct, then only one ray would come out. We'll see a teeny dot on the wall, right? Clear prediction, beautiful. And when you did that, Roberta is showing, you see the whole piece of paper illuminated, right?
Right.
Yeah.
Yes. And Andrew can do the same if he turns the light off. You're yeah. Yeah. Yes. See, you have a big blob of light on the wall, right? So obviously this model is rejected. And then the students come up with models that are on slide 25 and 28, kind of, I'm not sure about 25 would be my best. Let me see. Well, 25 is not, yeah, a few places have rays that go in multiple directions, and then we have reflections from the wall, which is good, right? But nowhere I see, a clear different model. So let's look. So on slide 29, we have these experiments that you just did, videoed, so you can look at them, of moving an obstacle closer and farther away from the bulb and making a hole so you can see it, right? But what the students do, I want to take you through their logical progression. And this is slide 30. In our activities, sometimes we give them two models to analyze and to test. This is another approach, right? You can give them two and ask them to test. But if I actually like better what we did, so people come up with a model, rule it out, and then come up with a new one. And this is the series of steps that students go through. Slide 31, these are the students observing what you observed, right? This is a group of students. Then they came up with this model the same way you came up with, and then they design an experiment. That's what they did, and that's what you do. That's what you did, right? So cover it and make a hole. And they make a prediction exactly as you did, that they will see a tiny spot on the wall. So this is them making the aluminum foil, and that's what they observed. Exactly what you saw with Roberta and Andrew's experiments, right?
I have a question.
Yes.
Do any students say that, well, if light only came out sort of radially, then you should only be able to see a small part of the bulb, but you can see the entire bulb, so...
Yes, yes. And if if they come up with this idea, that's great. That is one of the experiments, right? So we can run another experiment. It doesn't preclude us from doing this really cool experiments that most of the students come up. If they come up with them, we do them. If they come up with this reasoning, great. And everybody believes them, or they still want to do an experiment, right? So this rejects this model I'm just removing, and they came up with a new model. That's the model we want them to create, right? And and make the prediction that a large illuminated area of the wall will be. And what I want you to see is that these two models give you different predictions for the same experiment. Now think about when your students had an opportunity to use different models to make a prediction about an outcome of the same experiment. If this idea is correct, this is what should happen. If this idea is correct, this is what should happen. If you haven't been using our materials, probably never, because this development of hypothetical deductive reasoning is not a part of traditional physics learning experience. And rejecting something is also not a part. My experience with using this approach in an introductory course for engineers with senior physics majors working as instructors, telling me, Eugenia, I am in the 4th year of my physics degree. I've never had to reject anything. So that's why it is very important to give them an opportunity to come up with a wild idea, test it, rule it out, not feel bad about it, but feel that it is a part of the game and continue working. So what did we learn so far? And what is missing? Slide 42. So what did we learn so far about light? How do extended sources send light?
There's multiple rays from one location?
Yes, they send multiple rays from the same point, right? Why is it important for us as physics teachers? You would say, Eugene, you just spent 20 minutes on this idea. Like, who cares, right? Who cares? Tell me, why should you all care about it very much?
Because you're trying to build understanding and build meaning in their brain. in their head.
That's right. But I am talking about something really specific that we all teach and we want our students to understand. Why is it important to understand that every point of an extended light object sends rays, multiple rays in all directions, not just one ray?
Well, if we're moving on to lenses, they're going to have to use that anyway.
Right.
And actually, we don't. It's a really good point because we shift them to lenses and having the multiple rays from one point. And actually, the cognitive leap is assumed rather than actively taught.
Right.
But it is in.
And they only, and first I agree with you, it's lenses, but it's also mirrors, right? Curved mirrors, any images, telescopes, microscopes, medical professions, astronomers, nothing would work if each point sent only one ray, right? But when we draw this 3 rays for building images, they just take it as a given that there are 3 rays and no more. And that's why the research done by Lillian McDermott's group was when you cover half of the lens, you see half of the image. Is because students do not have this fundamental understanding. And so the purpose of this was to help you see how a very fundamental idea can be developed by students totally on their own. But remember, we started with the need to know. Remember the upside down thing? The candle upside down?
Right.
How did the candle upside down appear?
Eugenia, can I just say one thing quickly? Is that I was on a course in Oxford where they had various bits of experiments around, and they had half a lens, and it was still projecting a whole image. And it was to create a paradox. How can half a lens produce a full image? And actually, that's based on that lack of learning that you're addressing with this approach.
Well,
Yes.
I think also
build that.
Sorry.
Absolutely.
Sorry.
So now we return to our need to know, right? So why do we see the candle upside down?
Well, I was also, before we get to that, can I also point out that in textbooks, a lot of times it shows rays coming like directly into the lens, like a straight line of a ray going right into the lens, multiple of them going in the same direction instead of all going in, multiple rays in multiple directions through the lenses. So I think the students building misconceptions from previous things that they've seen as well contributes into this.
Yes, Roberta.
Can I ask if lenses are not part of the course, would I'm guessing you wouldn't skip it, but why would you not skip it?
It's not lenses, it's any mirrors, any optics. It's not just lenses, any image, flat mirrors, curved mirrors, lenses. If you're doing geometrical optics, you need this. If you're not doing geometrical optics, you don't need it. If you're not doing geometrical optics, you cannot teach wave optics or anything, right? So I don't know what kind of course would skip this part. Because again, any kind of optics requires this understanding. Okay, so let me try to use a whiteboard for our next thing to explain why we saw a new whiteboard. I don't know what is gonna happen if I can draw.
Eugenia, can I ask a follow-up on that last question, please?
I just had the thing here and then it disappeared. Oh, no. The tool board was here and then it disappeared. I cannot draw because I'm not the owner. Okay, forget it. How do I?
Can I ask a follow-up question on that last question?
Yeah, I'm going to, how do I get out of this whiteboard now? I need to get out of it and now I don't know how to.
Stop
Okay,
sharing.
yeah, I'm back. I'm back. Okay. Yes, another question.
So
Sorry.
I don't teach any optics, so I can see the value in this activity of teaching students that they can develop their own conceptions. Would you do this with students if you're teaching just solely a mechanics class?
Yeah, absolutely. We have all this developed in our mechanics materials, and you will see it in circular motion. I chose this topic for you to see how students test ideas and rule them out and everything. This is a workshop. It's not, you know, straight from kinematics.
Right, right. No, I was just
Right.
curious if you would still do this activity.
Yeah. Oh,
Or if you would do just something else that was more geared towards
yes, we
mechanics
do
that
something else. We have the whole chapter, first chapter of the active learning guide with these introductory activities. Okay, and it's all published, it's all put in the folder that you have access to. Active learning guide, online active learning, with all these introductory activities to get students thinking this way. And we usually do them in the workshop, but because we only have 4 hours, I chose an activity that is physics connected, not developing this
Right.
way of reasoning. Okay.
Excellent. Thank you.
Okay.
Actually,
Okay.
I just realized all the interference patterns that you need this understanding
Yes.
to understand
Yeah.
it.
Absolutely. That's why I said there's, if you're doing any optics, this is key. So, okay, I will try to do it on a slide. I am inserting a new slide. So you have a shape that is, I need, let me see, an arrow. So this is our candle, right? And I'm drawing on slide 44, and this is our screen. I'm drawing the screen with a little hole, right? So how come the candle on the wall comes upside down? Here's the wall. How would you explain it using our understanding?
You would draw it.
Yeah, draw it.
Well, it's because the rays are traveling on a straight path.
Okay, but that's not enough. If each point emits only one ray, you would probably see one teeny spot in the middle of this, right? No
Yes,
other
exactly.
rays would go through. But each point, remember, emits an infinite number of rays.
That's
So
right.
some of them will go through, but the ones that come from the bottom go to the top. And ones that come from the top goes to the bottom. That's why we have an upside down thing, right?
Yes.
Yes. So this is the foundation of what we know is a pinhole camera, right? And I put the slide here that was written by Andrew. Why should we care about pinhole cameras? This is a history for you. We're not going to read the slide now. But now you see how we constructed this whole idea of an extended light source using a very different approach to learning than all other, even reformed approaches. And how it is different, we will talk after a break. It's 11:01 on my screen, it's 01. So we come back in exactly 5 minutes. So 11:06, we're back. Take a break, eat, drink, pee, do jumping jacks, move, because we'll be sitting for another 3 hours. Okay, break. No. No questions. We are moving on. Everybody's back. Yes. Yes. Good. Very, very disciplined. Okay, let's go to slide 48. This slide represents the process that we went through figuring out how an extended light source emits light. I am giving you a minute to study it. Do you see the observational experiment that we did? With the bulb illuminating everything? This is after we created the model of a ray, right? The first model with the rays going in all directions from in one direction from each point. Testing experiment, rejection. Next model, you can continue testing it, did not reject, left it. Pinhole camera, practical application, as well as making images and everything. But do you see the logical progression? Yes, no, maybe so. Nod, yes. Okay, good. Good. Let's move to slide 49. How crucial was the idea of a ray to start developing this model? Absolutely necessary. And how important it is, the second representation with multiple rays coming from each point. So using graphical representations to help students develop understanding is another very important idea that we bring into our approach. The next slide shows another thing, is that on these activities, you worked in small groups, right? You shared, then we shared what each group did with the rest. And when you came up with the model that was rejected, it's not a bad thing. It's actually a good thing, right? Because that's how physics works. Physicists continuously improve their work, their models, their understanding, and nobody punishes them saying, oh, you did it on the second try, you're not going to get the Nobel Prize because you didn't get it on the first try. So this idea that you need to be correct on the first try, whether submitting your lab report or a quiz or a homework, contradicts science 300%. So not only we encourage students to improve their models and understanding in class, but we also encourage them to resubmit their work after our feedback. And we do not punish them by reducing their grade for the second or third try. There are different ways of setting up your classroom, but this is one of the fundamental ideas behind our work. That improvement, self-improvement, improving your work does not lead to a lower grade because you didn't get it on the first try. So you do not need to do the right thing from the beginning. All you need to do is to learn. And if you look at slide 51, this is just for you to remember what we did, how we went through these steps and where every experiment belongs. But what is important is slide 52. So ILE, or the Investigative Science Learning Environment approach to learning and teaching physics, is an intentional approach. So what does it mean, intentional? This is when no matter what you do, you have kind of a compass in your head. Does it involve students in developing in real science activities, in practices? And do students feel good about themselves while they are engaged in these practices. So two main intentionalities that students learn by engaging in the practices and activities that physicists engage in while learning physics. And they do not feel stupid doing it, but they feel smart and capable. They develop their growth mindset. Because if you think about our traditional physics education, not you, but the whole field of teaching physics or chemistry or biology, students learn it not through the practices of science, but through the practice of religion. A professor broadcasts the ultimate truths to them, maybe referring to some prophets. And then the students need to absorb these truths, believe in it, and practice. Totally religious experience. So instead of this religious experience, we want students to engage in the physics experience. And that's why experiment, reasoning, working in groups, improving their work. This is what physicists do. They don't sit and listen to colloquia. They do actually, and learn nothing from those colloquia unless the colloquium is in their area of expertise, right? I have attended hundreds of those. I only remembered astrophysics ones because that was my major, right? So listening and following instructions is not a practice of physics. And yet, for years, starting with, I don't know, 16th century or 17th century when natural philosophy started being taught, we followed this practice. Why? Because all the teachers were religious people. That's how they dealt with religion. And so they transformed these practices into learning natural philosophy, which became physics. That's my hypothesis, wild idea. And yes, it's kind of lecturing about active learning. So that's why I didn't tell you about how IEL works before you experienced it. I wanted you to participate, and then comes time for telling. And so keeping in mind these two intentionalities, I want you to reflect on what we did at slide 53 and put there, how is the intentionality of knowledge construction, how was it reflected in what we did? And how was the second intentionality reflected? You can put your thoughts there on the slide or say it, unmute yourself and say it. So what is it that we did that resembles science practice when we were figuring out how an extended light source sends light?
You asked us, how would we test it? When we came up with these hypotheses or these ideas, how would we test it? You know, put the foil over the top and really get out there and do it. The act of doing rather than just having it done to us.
Okay, that's one thing. What else?
We did so in a group.
Yes, you did it together.
Right.
You know, physicists do not work alone. And yet we require our students to learn by themselves. But learning is a social process. It's impossible to learn if you do not have anybody to talk to or bounce ideas off or discuss or anything. And yet we think that they should. And you know, the best practice is sit straight, do not move, and listen to me, right? Everything that is anti-learning is in this 5 seconds of an image of students sitting like this listening to a teacher, right? Okay, let's see what you're putting there. Yes, connect, very good. Yes, excellent. So you see it, right? But another important thing is very crucial that we never ask students to make predictions before observational experiments. They observe without fear of being wrong. And why? Two things. Well, physicists would not make predictions about something they have no clue. And secondly, is if you make a prediction and it doesn't happen, and the prediction is based on your intuition, then you feel kind of stupid. And especially it's true for women. they already have an imposter syndrome and people of color coming into a physics class, and once or twice they're wrong, they say, okay, well, I'm just stupid, I don't belong here, physics is not for me. So we want students to be successful from the very beginning. And observing and saying what you saw, everybody can be successful, right? Then we ask them to come up with wild ideas. Wild ideas means it's not your personal intuition. It's your imagination. It's your creativity. So you come up with wild ideas, then you test them. And because they're not your personal ideas, you just made them up. If you rule them out, it's a good thing. It doesn't hurt your self-esteem, but it also engages you in exactly the process that physicists go through when they construct and test their knowledge. And so these are probably the most fundamental differences between ISLE and a lot of reformed approaches that work on the formula predict, observe, explain. We do not do this formula. We do the formula observe, think, represent, come up with ideas, test them, hoping to rule them out, and then create new ideas. So this is our formula. But I'm warning you that it's not actually a formula. It is kind of steps that we follow, but it's not a linear progression. Yes, Andy, go for it.
Yeah, I just had a question. I mean, I love this approach, but how, in your experience, does it fit in when teachers are trying to put quite a whole lot of content into a small amount of time that's available? And also, then when you're talking about it being a collaborative experience, in the end, the student is sitting there as an individual and delivering what they know individually. I mean, is it the point, really? Yes, I get your religious aspect, that it evolved out of a kind of that kind of scholarship, but then our exam system is also evolved from that. Well, in the UK it has. So what's
yeah,
your
so I would say that many people who use through ISLE have group exams, and students work in groups. And I have a video of this group exam that you will watch later at the end of how students behave during this exam. You can have individual portion and group portion of the exam. Exams need to change. And cramming a lot of material, covering it is useless because students don't learn. We have evidence of it. I can address more, this thing about coverage. I don't want to do it now yet. I want you to see how the system works, and then we will discuss it, okay?
Yep,
this is the first question that comes up in every talk, in every workshop. How do you cover the material? And I want to say, I don't want to cover. I want to help them uncover. And that is a different approach to learning. That is traditional, and traditional approach does not work. We have evidence now, right? It doesn't. Students don't learn. So we want them to learn. Let them learn. Andy, I want to come up to it later. We probably will have time for questions after. Okay? Okay. So there's another difference between ISLE and most of reformed approaches, at least used in colleges now. And this approach is a flipped classroom. Flipped classroom means that you read a textbook before coming to class, or you watch a video of a professor explaining stuff to you. Then you come to class and you work on some questions that the professor asks, you participate in discussions. While it is better than traditional instruction, we reject this approach because it's still a religious experience. You read something else written by somebody without any experience with it, right? It's like reading Cliff Notes about War and Peace, not Cliff Notes, but commentary about War and Peace without actually reading War and Peace itself, right? So we pay a lot of attention to students working with a textbook, and I'm going to show you how we do it. But we have a textbook that is ISLE consistent in every chapter, where students see where knowledge comes from, but they read this textbook after doing activities in class, after having experiences, after creating images, and we teach them a very important method of how to work with the textbook. And so I would like you, oh, you know what? Let's go to slide 55. So why is it important to learn how to read a textbook in a physics course? Tell me why. What do you think?
At some point, you're going to have to read a book to learn how to do something.
Right. It's because scientific texts are not fiction. Our students are expert in reading fiction, and they also are kind of experts on reading games manuals, which are huge, right? So those who read game manuals are better suited, are better prepared to read scientific texts. But we will assume that it is a skill that still needs to be taught, right? So because it's a part of the work of scientists, they read papers, they share their ideas, but most importantly, our students are in college taking other courses or will go to college. So reading scientific texts is a very important thing. So how do we teach them to read scientific text? First, we wrote a book that is suitable for this reading, and it's slide 56. This is the textbook that you all got access to. If you're teaching in high school, there's AP edition. It has no difference between regular and AP, except in the AP edition, it says how it matches with AP stuff. All the text is the same. So if you look at the cover of this book, you will see our intentionalities right there. And it's like, what? Where are the intentionalities in the cover? It's a girl on a bicycle with a backpack going to town, right? You see the girl. One of my sons said, Mom, your book will be called a butt book. But nobody did that, said that yet. So what is this cover saying to a student? That everybody is welcome to physics, including women, right? That you learn physics in college, that's why the backpack. You explore the physics there, and then you go to town to apply it. So this cover has very deep meaning, and I want you, when you open your ebook, to look at the cover and think about it, right? But now about the method of reading. It's called elaborative interrogation, and it was shown by research, slide 57, to be the most effective way of learning from a scientific text. This is what we all do when we read papers or books of physics books. What we do, we read a sentence and then ask ourselves, how do I know it's true? Does it make sense to me? And does it make sense means, does it relate to something I know? Does it describe something that I can imagine? And so this elaborative interrogation that we experts do naturally and subconsciously, students do not do. When they read a textbook, they read it as a fiction, as a novel. And of course, if you do not ask yourself about each sentence, how do we know it's true? Then all reading becomes meaningless. And that's why the students say that textbooks are useless. It's not because they're useless. It's because we did not teach them how to read them. And so how do we teach them? We tell them about the elaborative interrogation, that you need to interrogate the text, and we show them how to do it. I've been doing it with my high school students 40 years ago. I would literally open their textbook on a random page that is related to what they're learning. I say, let me show you how I read the textbook. I didn't know the term elaborative interrogation at that time because the paper about it that we use as a source of data was published 30 years later, but I still did it intuitively. So this is slide 58. This is, I want you all to read this, little text written there. And remember, you read it after you did this experiment. Ready? No? Raise your virtual hand if you are done reading. And I'm not following the chat at all. my bandwidth is not wide enough. So whatever you're chatting, I will look later. Sorry. Finish reading? Yes? Okay. So that is what I would do in class if I were to teach my students to interrogate this text. Is that okay? Let's open the page and read it. A laser pointer is useful for studying light propagation because it emits light, because the emitted light emerges as one narrow beam. Yeah, we just did this experiment and actually we saw the beam, so that is true. However, most light sources, such as light bulbs and candles, do not emit light as a single beam. How do I know this? We did the experiment, turned the light bulb on, and everything was illuminated. But I forgot what we did after. Let me read some more. These extended light sources, okay, they're called extended light sources, bolded, so that's what it is, consist of multiple points. Each of them emits light. Is that right? Yes, I remember. So we drew a picture and we put a ray from each point. Yes, each of them emitted light. I remember that. When we turn on a light bulb in a dark room, bulb sends light in all directions. But does one point of the shining bulb send light in one direction, or does each point send light in multiple directions? Yeah, I remember we did that. So what did, oh, yes, we rejected the idea because the light coming from the hole illuminated the wall. So then we decided that each point sends multiple rays. Now remember the experiment. Both of these ideas can, does one point of the shining bulb send light in one direction, or does each point send light in multiple directions? Both of these ideas can explain why the walls, floor, and the ceiling are illuminated. Right, even if it's one ray from each point, then you can still make all walls lit up. Let's investigate two possible models of how extended sources emit light. Yeah, that's exactly what we did. We investigated. So that sentence is true. To do this, we represent the travel of light from one location to another with a light ray drawn as a straight line and an arrow. Boom, boom, boom. Are you getting the point? Stop after every sentence and ask yourself, how do you know it's true? Do I know this word? Did we do this experiment? If now imagine the students did not do these experiments, what would they get from reading this text? That's why it is important that they have experience. And you might be thinking, what if I have 300 students? That's fine. They can still do these experiments by observing them and suggesting ideas and everything. But what I wanted you to see is how this interrogation method works. So now, if you look at our textbook, you will see that at the end of each section, there are these interrogation questions. you know, we said this, why is it true, or how to explain this, and so on and so forth. But we also give assignments when we give them statements from the book and asking why is this true explicitly. And sometimes we change them and asking why is it not true. Larry, you have a hand there. I don't know if this is an old hand or a new hand, and I don't see your video. So Larry? No. No response. Okay, slide 59. I want you to read it and tell me if it makes sense. Interrogate it. Does it make sense?
Not the last sentence, not the last bullet point.
Yes?
Yeah, I guess I would agree. I'm not quite sure what the last bullet point is saying.
What the last bullet says. Okay. This is
Get rid of the word not.
the answer to Andy. So imagine you've been teaching through this approach for 6 months. The students understand observational experiments, developing models, multiple representations, all this process, right? And you're worried that you don't have time for them to do everything in class. Then you say, now that you have mastered the process of science and interrogation techniques, I am assigning you to study on your own this particular section or chapter. And what you need to do is make a list of interrogation questions that you could not find the answers to in the text. And I would choose the text that doesn't have complicated experiments or whatever it is that, or they had videos like here, there's no video, but we have a lot of sections with observational testing experiment tables with the videos that they can actually experience. But this can only be done after they have experience both with the process and interrogation technique. And this is one of the ways to cut time. Because think about our students who learned so many things in life without anyone teaching them anything, right? They can operate a new cell phone 10 million times faster than you can. They can figure out how to use this piece of software faster than you. Why? Because they taught themselves how to do these kinds of things. I'm not even talking about skateboarding and chess and music, right? So they are expert learners. But for this particular kind of learning, you need ideas of how the system works, right? And the system works according to this picture of observing, coming up with ideas, testing them, applying them, blah, 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 right? And you're learning about it by interrogating everything. Have you ever been to a physics meeting, like conference? Have you? Yeah. What happens after every talk? Massive interrogation of the presenter, right? How do you know this? Did you do this? Why do you believe in this? This is all natural interrogation techniques that physicists use. So now I want you to go up to slide 54. I also want you to raise your hands if you teach in a large class. Does anyone teach more than 50 students at a time? Teach classes that have 200, 300 students? I don't think anyone, right? Everybody here teaches small classes. High school or 2-year college. So why is ISLE uniquely suited for small classes? As I said, it can be used in large classes and many large courses use it, but it is uniquely suited for small classes. And slide 54 answers these questions. So I want you to interrogate this slide and ask, why is this true? Why is the first bullet true? Why is the second bullet true? So interrogate and ask a question. You ready to interrogate the first bullet? So why is the first one true? You can unmute yourself and
You
say
don't
it.
need so much equipment.
Yes, you don't need so
Yeah,
much
a lot
equipment.
of equipment.
And what is important here, that you can have lab type experience before you have a discussion, because you have a small class. You don't need to split it into lectures, labs, and recitations, which is a silly split, because physics is not split like this. Physics is a process. But you can't follow this process if students doing in the labs something else, not related at all, and then all they learn physics is from a lecturer, right? So that's why incorporating labs into the process smoothly when they need it is crucial. And it's easy to do when you're teaching a small class. I also said it's uniquely suited for diverse student population, topic for different workshop. But why do you think it is suited for diverse populations?
Because it welcomes everybody in. That
Yes.
everybody can do this. Everybody can grab the equipment and turn on the laser or turn on the light bulb. Everybody can do that.
Right. And because we ask them when they do observational experiments to say what they saw only in simple words, second language speakers can use their vocabulary to do this. They can draw with multiple representations, and we don't make them fail. And this is the fact that students fail is the most important issue in physics. We make them physics impaired, right? That I cannot do physics because of our teaching methods, not because of their abilities. So that's why it is suited for diverse populations. Even more, I worked with an expert in disability studies, and she said that ISLE is an example of universal design for education. You know what universal design is when you have sidewalks that are, you can go with ramps for people in wheelchairs, when you have these little bubbles for blind people to know the sidewalk. And so why are they there? It's because at some point architects decided that we do not need to change people to be successful in our society. We need to change the environment. And so anyone can be successful. Anyone can push the button in the elevator, even if they're blind, because there's Braille symbols there, right? Anybody can climb into a bus because a bus has a special lift. And so this is an example of universal design. And we are creating this universal design for education as changing the environment. That's why it's called an environment, right? We're changing the environment, not the student, to make everybody successful. Okay.
I would like to
Yes.
argue too that not only do you need diverse, like, does it work for diverse populations? Sometimes you almost need them, because what students bring to the table is their different backgrounds and different experiences. And when you're asked them to attempting to solve different ideas, if they're too uniform in their background, they tend to be limited in the ideas that they think of. And by having the multiple backgrounds, they get a wider variety.
Absolutely. 300% with you. Yes. Yes. It's not right. I agree. Okay.
Can I just say something? It's the
Yes.
first time that I'm teaching IEL from September. I have a class of 20 higher level students. The first time since I've been teaching that nobody drops down to standard level. Such a big class. It always happens. Nobody's dropped down so far.
That's amazing. That's amazing. Oh, I'm so happy for you. And okay, one person can teach all components. You understand, you don't have TAs like people have in large enrollment courses. You are in charge. You decide what to do. And another, the four, that you know what happens yesterday. So what I mean is that when you have a professor, a TA, and the lab TA, they don't know what happened in a it's all disconnected, right? Here you're one person, you follow the same philosophy, you use the same language. There's no, you do not make it more complicated for the students than it needs to be because you're one person in charge, right? And you don't need to convince anybody that it's a good approach. If you believe in it, you do it, right? Easier to deal with groups, with small groups and the whiteboards. And we use very cheap equipment. So you don't need expensive stuff if you don't have it. Okay.
Can I throw in a comment here?
Convincing? Is that convincing?
Can I throw in a comment?
Yeah. Go ahead.
So I guess I would agree that implementing an IEL approach is easier for smaller classes than larger classes. But unless you're like a one-person physics department, which definitely exists, but sometimes there are more than one, you may not have quite all the freedoms that.
Well, you know.
But it's easier. It's easier than a large university.
Yes.
Definitely.
Yes. Yes, of course. You know, take everything with a grain of salt. Good. Okay. So now we are it says a break, but I think that we can actually start a little bit because we are moving much nicer. It means we'll have more time for questions, right? Okay, so let's go to slide 61. And what we're going to start now is, before we did an example that had only conceptual development, right? Now we're moving into an example where students develop mathematical tools and use them, and complicated conceptual tools, right? So that's why I wanted you to read chapters 2 and 3 in the textbook. Please raise your hands, those who did. Okay, everybody did. Okay, great, great. So in order to start, I want you to go to slide 62 and see what students should know before we start. So we are going to talk about the topic of circular motion at constant speed, okay? That would be our next big idea. So this is what students should know before they do kinematics, Newton's laws in 2 dimensions, right? This is chapter 5 in the textbook, right? So look at slide 62. Oh, thank you. Okay, does that make sense? Okay, and slide 63 is a reminder of how to draw a force diagram. So we do not use the word weight. We do not say the force of. We say force that Earth exerts on an object, or force exerted by Earth on the object, force exerted by the rope on the person, or whatever it is, right? It is 2 subscripts, and I just saw sometimes we have to claim our freedoms. Yes, absolutely. Okay. So, need to know. I want you to go to slide 64. And this is a video that I didn't think we would have time to watch And we probably shouldn't, but it involves a person, Damian Walters, who is running loop the loop. And I put 2 screenshots of him running upside down. Do you see it? If you watch the whole video, it's about 3 minutes. I don't want to spend them, but it is what he's trying to do. Is how fast does he need to run to be able to run loop the loop upside down? So this is our need to know. We're going to answer this question later, but now we are going to take a break and start this unit after the break. So on my clock, on my computer, it's 46 minutes after some hour. Let's come back at 51 minutes. Okay? You all here? Yeah. Come back, people. Start. Okay. Is everybody back? So the need to know, as I said, is to explain how can a person run upside down, right? And we see in the video, if you watch a video, that he tried many times and he would fall off, and then eventually he made it. So it's like really, it's not an easy thing. So to explain why he needed to run so fast, we are going to start studying circular motion. So remember, we are familiar with force diagrams and Newton's laws and everything. What I want you to do is to watch the videos. And in fact, in class, students do 2 of those experiments. And the third one, you know, all my high school physics teachers who I prepared, and this is like over 170 of them, they all rollerblade and actually do this experiment. But if you don't rollerblade in class, or you don't have room, then you can show the video. Okay, but the first 2 experiments, it's crucial that you get the students to actually do them. Okay, so I am starting the groups, and I'm giving you 10 minutes to do this. Okay, each room has a slide, and you use arrows and text boxes to label your force diagrams. Okay. Yeah.
Okay.
Okay, everybody here?
Some
So
people
I
are
want you to look
skilled.
at the slides, and I know that one room did not finish. And this is what is going to happen in your lessons. So you have one group, one team that is a little bit behind. Do you wait for them to finish before you move on, or you move on when the majority is finished? As long as it's not the same team that is always behind, I would move on because they will catch up. They had the experience, they thought about it. When they see others work, they say, yeah, that totally makes sense. If they didn't have time to put it on the board, it's fine because you're not grading those boards ever. This is a learning experience. So what students do, they either go around and look at others' boards if they're different, or they lift the boards. Everybody lifts the boards if they're the same, and they're pretty much the same now, except one rebel group had the circle on the other side, on the right, not on the left. But if you look at the boards, they're all the same, right? So we don't need to present. We just want to confirm that what we did is correct, or if we didn't have time to do it, then we know how to do it, right? So what did we find from this analysis? And this is, I just want to remove the cover from slide 70 because these are my force diagrams. Actually, I didn't draw them. My husband, Goris Planinsik, drew them. He's a co-author on the textbook and all my adventures, but he's really good with graphics. So he made these great arrows that I would never be able to do. This is what you all did, right? So let's go to slide 71 and try to summarize the pattern in words. Andy, you have a hand?
Yeah, sorry. I just wondered, do you see value in keeping the group members the same or frequently varying them? Just having said that, I think two members of our group at least were way better than me, and I'm feeling. I'm just saying, in the class, I'm thinking, would you switch people around or have them just catch up? I don't want to be.
Yeah, switch people around during the activity?
No, I mean, as you're running through the session, if you've got several
through the
points where
session, I wouldn't. Through a lesson, I wouldn't change the groups. And some people keep the groups for a couple of weeks or a semester, depending on your preferences. If the groups are working, then it's fine. If they're not working, I would just do the random assignment every class or every other class. But research shows that random assignment is the most productive assignment. So don't try to put, knowledgeable and not knowledgeable and mix them out. Just do it randomly and change it and it will be fine. If the activities are meaningful, the groups will work. If the activities are boring and useless, the groups will not work. And there are also stuff about working in groups that is important that we can talk about if we have time. But I would say either way is fine. So, okay, summarize the patterns that you found in words. Could you please do it, somebody?
The net force pointed towards the center of the path.
Right. So the sum of the forces, we actually avoid the term net force because students think that the net force is an additional force. So the sum of the forces, and we do not ever use the term centripetal force. It is not a part of our vernacular for exactly the same reason. You give it a name, they think it's a special force. So we only talk in all our mechanics and E&M, everything, the sum of the forces. Okay, but we understand when Mark said, net force, right? So the sum of the force towards the center. You should see the students trying to get this, the bowling ball roll in a circle. That is the most meaningful experience. That guy who was doing it, he did it for 40 minutes before he could actually get it to do. I can never do it. So the trick is that the ball needs to be moving fast enough, and it has to be a bowling ball on a smooth floor. Why fast enough? And that's what I learned by rollerblading and using bowling balls. So if you have a bowling ball that moves slowly, it goes over each bump in the floor, and you have this conversion of kinetic energy into internal energy very quickly, it stops. But if it moves fast, it flies over the bumps, and then it moves at constant speed. The same with rollerblading. If you do rollerblading and you want to do this circular motion experiment or any kind of experiment for Newton's second law, if you move fast, the friction is almost negligible. If you move slowly, it's very significant. It's the bumps that matter. So you want the bowling ball to fly over them, so the initial speed needs to be high. And the students figure it all out. You just give them the bowling balls, which are discarded in bowling alleys often. Just go to any bowling alley and say, do you have any balls that you don't need? And you'll get them for free. Don't buy them, of course. And any mallets, any sticks will do. But it's a great experience, kinesthetic experience for the students. Okay, so the sum of the forces is towards the center. But that is our hypothesis, right? Let's test it. Let's test it. So here's slide 72. So we want you to think of, and this is together, right? First, why would the ball roll inside the ring? And second, what would happen if you remove the part of the ring? But I want you to make the explanation and prediction of what will happen if we remove the part of the ring, using this idea that when an object moves in a circle at constant speed, the some of the forces point towards the center. That is our hypothesis, right? So what do you say? Why would the ball roll inside the ring?
It's
Being
going to
pushed
keep going the way it was going and keep following the circle. Because isn't that what we said in Newton's first law, that a ball will just keep going the way it's supposed to go, right? So it was going in a circle before, so it should just keep going in a circle, right?
Why would it go in a circle? Newton's first law says that for an observer in inertial reference frame, an object goes in a straight line with constant velocity if there are no forces. So it does not continue any motion it had before, only the motion straight line, and if it's not interacting with any other objects, or the sum of the forces is 0. So, but if we roll a ball inside, why should it continue rolling in a circle?
The wall is pushing it.
How is the wall pushing the ball that is trying to get out?
It's changing the direction as it moves.
Why would it change the direction?
The force
How
change
is the
direction.
how is the ring interacting with the ball?
The normal force is pushing it.
Yeah, perpendicular,
Sure.
right? The
Yeah.
ring can only push perpendicular,
Push.
right? And perpendicular is towards the center.
Right.
So if we let it roll, then the ring will continue pushing it. So it is not the first law, right? What kind of law is it? Second, yes, it's the second law, right? The force leads to change in motion. Okay, great. But what would happen if we remove part of the ring?
There's
The
no
ball
force.
would try to go straight.
Yeah, it will go. Why would it go straight?
Nothing's pushing on it anymore.
Right. Nothing is pushing on it anymore. Okay, let's look at the reasoning that we want our students to do. So this is slide 73, right? So if the ring is to the left, then the force that the ring exerts is perpendicular to the ring, right? So it should be a straight path. So that's how we want the students to reason. So why don't you go to the next slide? 74 and watch the video.
Join Planet Fitness during the Big Fitness Energy Sale and save big. Deal ends Friday, February 16th.
And that is the commercial from YouTube. Sorry. We have a good video, but it's not as good as this one. This is an improved video. That's why it's on YouTube, not in the materials yet. Yeah, I like Joe. That pipe pan. So, did it work? Yeah. So we didn't disprove this idea yet, but sometimes we need to think why this idea makes sense, right? Why should the sum of the forces be pointed towards the center when an object is moving in a circle? Why should it be? What do you think? Is that like a completely crazy thing that we found, or it makes sense? Does it make sense to you that the sum of the forces is towards the center?
Yes, because it's changing direction to go towards the center.
Right? Because the ball that is, or an object that is moving in a circle is constantly changing direction. So what is the direction of the ball at each moment? Let's see. If you go to slide 75, there is a YouTube video where I use a meter stick to show the direction of my motion. I hold it very tightly against my side, and I try not to wiggle it, and I move in a circle. So every time I move, this meter stick shows the direction. Are you watching the movie?
Yes.
I do it actually in class on rollerblades. Somebody is pulling me in or I go in a circle and I hold the meter stick. It's very impressive. You don't have rollerblades, you just walk, or a student walks. Rollerblades are just for looking at in a little juicier than just walking. So what do you see? What is the direction of velocity when an object moves in a circle?
Tangent to the surface.
Tangent to the circle, right? So if the direction of velocity changes all the time, then what does the object have, even if it moves at constant speed?
Acceleration.
It has acceleration, right? It has acceleration. So if our idea that we have not rejected yet, that the sum of the forces points towards the center, then where should the acceleration point, assuming Newton's laws work for circular motion too? Towards the center, right? So this is our crazy idea that the acceleration needs to point towards the center too. But how do we find the direction of acceleration if we only dealt with acceleration of the motion along a straight line? So I'm going to help you a little bit to show you the trick, okay? And the trick is on slide 76. So you see a car going in a circle, right? And we want to know the direction of acceleration at the point marked at step 1. Do you see it? I can't see you now because I'm looking at the slide, so you have to say it. Do you see that point?
Yes.
Yes. Okay.
Yes.
Do you see the velocity vector right before it? It says V initial, and right after. So
Yes.
what we want to do, we remember that acceleration is velocity final minus initial divided by the time interval. So the direction of acceleration is the same as the direction of the delta V arrow. So what we do, we put the initial vector on the side. This is step 2, and final vector, and we put them tail to tail. And then we look what vector we need to add to the initial vector to get the final vector, just as we did along a straight line. Do you see it?
Yep.
And this delta V direction is the same as the direction of acceleration because delta T is a scalar, right? So now I want you to practice this method, remembering that because it's a motion with changing velocity, these 2 points for initial and final have to be very close to the point where we want to determine the acceleration. Does that make sense?
Yes.
They're not far away, they're close.
Right.
And we see how the velocity changes. And you saw it with my meter stick, right? So how do we get from this to this? We have to pull this vector somehow towards the center, right? That's what the force is doing. So it's all making physical sense. Okay, I'm going to put you in the rooms for 5 minutes, and each room has 1 point in a circle, okay, that you need to figure out how to do the acceleration on the slide. So that's like a more difficult thing than on the whiteboard, but that's just the way it is. We're gonna help. 5 minutes. Let's do it. Drink. Yeah. Oh, I hope that part was not recorded.
We're passing around alcohol now. I see.
Now, Chris said that you will need to fill out the evaluation and she will share it with me. And I said, no, no, no. Okay. Okay. So I apologize that you have to work on the slides instead of a whiteboard where it would be very easy and quick, but that's just Zoom making our life more difficult. But what did you find? If you look at all the slides, what can you say about the direction of acceleration?
It's towards the center of the circle.
It's towards the center of the circle, right? But
Yep.
look at this now as teachers. I did not say a word. I did not say a word about the forces. I did not say a word about the acceleration, nothing, not velocity. You did everything. And the students do it too. You just need a few hints. So the hint is that put the points close to the point where you want to find the acceleration. Another hint is draw the velocity vectors longer, not very small. It's easier, right? But that's it. You as students came up with all the fundamental ideas of circular motion, right? So if you go to slide 82, you will find my weak attempt to do the same for point D. So I marked those 2 points for initial and final, and the acceleration is towards the center. So, slide 83, does it make sense? Yes?
Yeah.
Yeah. Now it so makes sense. It's just no point in even talking about it, right? Like beating a dead horse. Towards the center already, everything. No problem. Understand why. But can we explain why Damian Walters needed to run at a certain speed not to fall off the loop?
Not yet.
Not yet. Why? What is missing?
The magnitudes.
The magnitudes, right? We don't know what the acceleration is, right?
Right.
We don't
Is that
know
the
how
right
the
speed?
speed and acceleration are connected. So let's move. I'm going to skip one of the activities here. And if we have time, we'll come back to it. We're going to slide 87. So this acceleration we call radial because it points towards the center. So from your experience, if you rode a bicycle, drove a car, rollerbladed, trying to make a turn, what are you trying to do when you are moving in a circle to be successful?
You push out.
Yeah, you push out if you're on rollerblades, but concerning quantities.
Moving slow.
Slow, yes. You want to move slow when you enter a curve, right? That's why when you go on an exit, you have to reduce the speed from 65 miles an hour, at least here. If you're in Montana, it would be like 80 miles an hour to 45 or 25 miles an hour, right? So you know that to negotiate a turn, you have to move slowly, right? So it means that when your speed is faster, it's harder to do it, right? But what else do you know about the turns? What turns are easier to negotiate and what turns are harder?
How sharp the turn is.
Yes, how sharp the turn is, right? And the sharp turn has a small radius and not so sharp turn has a larger radius, right? So how do you think, and this is just, hypothetical thinking, how would this speed and radius affect acceleration?
Lesser the radius, lesser the speed.
So the less the speed, it's easier to negotiate. So it means that acceleration will be less. But the less the radius,
harder.
the harder, right? So acceleration should
Yeah.
somehow depend inversely on the radius, but we don't know first power, second power, third power, and somehow depend, I don't know, not linearly, but on the top of the fraction, right? The numerator part of a fraction on the speed. Okay, so now I'm going to give you 15 minutes because we have time for my most favorite activities. It is 2 activities together on slide 88 and 89. It is conceptual reasoning of what the acceleration depends on. And disregard the timing because we're ahead of time. And I thought we wouldn't have time for it, but we do. So let's do it. So I'm giving you 10, did I say 15 minutes?
15, yeah.
15 minutes to work through these 2 activities on the slide for your team. Okay, 15 minutes. So now it's 32 minutes. So at 47 minutes after the hour. Okay. So what did you manage to do? And I would like you to look at a slide of, you know, people drew and wrote. Let's look at the slide of team 4.
Nice.
And this is 94, right? So what they did, they showed that the delta V arrow is proportional to V, right?
Right.
So when V doubles, delta V doubles. When V triples, delta V triples. Do you see it clearly from the picture?
Yep.
Right. So we can say that if acceleration were only dependent on delta V, would be equal to delta V, then it would be proportional to V. But acceleration is not delta V. It is delta V over delta T. And then if you go to slide 93, you will see how delta T affects, this is team 3, how delta T affects it. Not only when the speed doubles, delta V doubles, but delta T halves, right? So delta V over delta T is 4 times more. And when the speed triples, not only delta V triples, according to slide 94, but the delta T is 1/3. So delta V over delta T becomes 9 times more. And so we can say now that acceleration is proportional to what?
V squared.
V squared, right? And we have this understanding now, not because, so think about velocity vector that you need to turn, right? If the velocity is longer, so not can be this small or this small, then the delta V, the change in velocity becomes bigger, right? But when the velocity is longer, it also moves faster. So you need to change velocity faster when it moves faster. So this physical feeling for what acceleration is, it's not just the change in velocity, it's how fast this change happens, affects the acceleration, right? But if you look at slide 94, you will see this team finished. What happens when the radius is more? Can somebody from team 4 explain how they did the second activity?
Yeah, so if R increases, then the path length would also increase. And so for traveling, at a constant speed, then it would take longer to go around.
Right? And
And it
that's
seems
why,
like if R doubles, then the arc length doubles and so on and
right.
so forth.
Then the time. So now we here only have the time, right? If you have a longer arc, the time is longer. So that's why the acceleration depends on the inverse of the radius. And this is slide 94. So what did we learn? That acceleration is directly proportional to V. I don't know how to do it. I'll just do it like this. V squared proportional, right? And inversely proportional to R. Agree? People?
Yes.
Yes,
Yep.
yes. So we all agree with that. Now, what is the coefficient? Oh, before the coefficient. Okay, sorry. I skipped one step. So it's directly proportional to V squared, inversely proportional to R. How do we combine them together? To say
over R.
V squared over R, right? Why do we combine them as V squared over R? Like, why is that?
So you just get one equation? I don't know.
Right. Why don't we say minus or plus? Okay, it's the same thing. It's not working again. Can you stop? Somebody is sharing the whiteboard. Please don't. I cannot type on it. It's the same bad thing.
I'm trying to look at it. I don't know how to get into it.
Okay, thank you. I don't know who
Mhm.
started. No, it's the same unworkable whiteboard. So how do we know that we need to put it as a ratio? Why not subtract?
Maybe the relation between the, if you plot the graph between the acceleration and velocity square, maybe the graph can give you the slope 1 over R.
Right, but we're not collecting data. I'm just asking, we reasoned that it is directly proportional to V squared and inversely proportional to R. How do we know that we need to divide V squared over R to get the total proportionality?
Because that maintains the relationships in a single equation with the new constant.
Right. It's because we cannot subtract because they're different units, right? And in physics, we cannot subtract meters from meters squared per second squared, right? We can only deal with either multiplication or division, right? And if we multiply, then with the increase of R, we will not get the inverse proportionality, right? So with the increase of R, we'll get the increase of acceleration, while now we know it has to decrease. That's why it's a ratio. So it's really important for the student to have a discussion. How do we come up with a pre-final expression? Pre-final because we don't know the coefficient. Another thing that is important is to say that when we do division in mathematics, a division is a continuous subtraction. For example, how do we divide 15 by 3, right? We say, okay, we take 1, 3, and we are with 12, and then we take another 12, and we're with 9. So we need to take 3 5 times from 15, right? And that's what division is. It's taking away, and multiplication is adding. But when in physics, when we divide or multiply quantities with different units, it's not more of the same quantity. We get a new quantity at the end. So that's why when we divide meters squared per second squared by meters, we do not have fewer meters per second squared. We have a new quantity. And what is the units for this quantity? Meters per second squared, right? So that already starts making sense. That is the units of acceleration. So we're not like really crazy coming up with this relationship. These are the units of acceleration. So we gain confidence that we're on the right track. Yes, right, Andy.
I'm just wondering, is it better to, I get the unit analysis there, but surely if you're adding them or subtracting them, you're introducing a constant, a value that stops it being proportional to one or the other.
Right. Absolutely.
Rather than a dimensional argument.
Any way that it works for you is fine, as long as, yeah, anyway, I'm not saying one is better than the other, but we still, so we got the units right, so we gain confidence, but we still don't know what the coefficient is, right? So in physics, and as you know, Galileo proposed an Occam razor idea a long time ago. So when we are hypothesizing something, we need to come up with the easiest possible solution. Start with the easiest possible solution. So what is the easiest coefficient that we can think about?
One.
One, right. One is the easiest coefficient, right? So let's have this hypothesis that coefficient is 1. And now we're going to test this hypothesis that the acceleration is actually equal to v squared over r, not directly proportional. Is that clear? And to do this, there is a, here is a lab, but virtual lab, but we have really great lab activity also with the conical pendulum in the active learning guide. So go for it. Anya is taking charge with it. We are still working in different rooms. I want you to read it in order to, before I send you to the room, so you ask questions if they have questions, if you have questions. So let's see how much time we take. And if you need to get up during this teamwork, please get up, go to the bathroom, grab some food. I said the end time with the discussion is 1:25. So try to end by 1:20, okay? Which will give you 20 minutes. Okay.
Yeah, okay.
Uh-oh.
Yeah, that's
Oh,
okay.
Oh no.
You didn't take the screenshot?
Oh, we forgot.
Oh.
No.
Oh no.
Oh no.
Well, that will not happen in a real classroom, so don't worry about it. But yeah, I saw your work. When it says that the rooms will close, you need to take a screenshot with whatever you have.
Oh my God, it's
Oh
all
no.
gone.
No.
It's not there anymore. Okay. Please stop.
But now I can do it. But now it works, actually. Okay.
Okay. Anna, would you please take over?
Okay, yes. So that is kind of the slide 104. That is kind of showing the solutions, well, what we expect for students. But I think that, well, most of you did. I think that I'm just checking.
No,
what
that
team
everybody
you
did
were.
the beginning.
Yeah, yeah.
And slide 105 is also everybody did. So
Yeah.
it's 106 and forward.
106. Yeah, so that is the prediction about what happens with the angle, and substituting instead of v squared. So the expression was v squared over gr, right? And we substitute period in all other variables, radius and period. And then you need to do the, well, we ask students to do unit analysis and to see that tangent is indeed dimensionless. And then check what happens if the period is infinity. Then tangent is 0. And if tangent of theta is 0, that theta is 0, so there is no rotation, right? It's very slow. Or when the rotation is very fast and the period is 0, then tangent turned into infinity and theta is 90 degrees. So it's moving, which makes sense. Well, conceptually, I mean, from intuitively. And here we does see that the expression that mass cancels out. So I always encourage students to not plug in numbers from the very beginning, but come with the expression with symbols, so they could see that the final expression indeed doesn't depend on mass. And then already after you come with a general expression, plugging in all the numbers, measuring for 40 frames, getting the value, and see the angle with uncertainty. Here is again, there is an important point that students have tendency to tell that, yeah, it's close enough to getting the values. And there is one more step to estimate uncertainty. And here we estimated plus minus 2 degrees. I don't think that, Eugenia, we probably don't have much time to discuss about error and how to deal with errors and uncertainties.
Not today.
Not
it's a
today,
different workshop.
Right, it's the whole workshop. But yeah, we'll always encourage, well, we're always talking with students that, yeah, it should be done, otherwise you cannot compare the values. And just saying roughly the same, it doesn't work.
Can I ask a question? How did you measure the radius by counting pixels? What do you mean by that? Because that's where we got stuck. We didn't know how to measure the radius.
So
Can somebody say, those who did measure the radius, how they did it?
Yeah.
Yeah, go ahead.
What we did was we stopped the frame. We found the scale, and basically there were 2 marks on the top that said 12 centimeters for them. So on one of our screens, we measured it with a ruler, and then measured the distance of the ball to the center with the ruler again, and found the ratio.
Very good. Thank you. So we wanted you to go through this exercise, although all of you can solve the problem, to see what kind of mathematical sophistication the students can reach after going through this process. So you don't think that the IEL approach is all conceptual. We actually do pretty sophisticated mathematics, and this is not the most difficult problem. This is like a lab exercise because you're collecting data, evaluating uncertainties. But Anna, with her experience using teaching in a 2-year college, created slide 110, emphasizing difficulties with math that 2-year college and high school students might have, students might experience, and all of those are addressed in our materials. So if you feel like your students are having these difficulties, if you use our materials, they will be addressed. There's a question, is IEL approach generally done in a combined lab? Yes. Yes, it is. And that's what we said from the beginning. It is not a lab lecture course. When it's a 2-year college, it's gotta be a studio classroom. Because when we, in a large enrollment course, it makes sense to have labs separately. But in a small course, when you have 20 or 30 students, you can run it as a continuum. And yes, you have to start in a lab and end in a lab, and then whatever discussion is in between. So you cannot just have a lab course that is dissociated from discussion and solving problems. You need to have them all integrated. The fact that most of our courses, not in high school, but in colleges, have a separation between a lab course and the lecture course is, again, following up all traditions that do not help students learn. So look at this slide, and then we have more materials, explaining how to help students with mathematics. So the next slide is 111, is at this moment, students are ready to return to the need to know and explain how how fast he needs to run in order to make loop the loop. We're not going to do it here, but you see the progression. What we're going to do now is to talk about something that will come up in your course if you use IEL or any interactive approach. And that's what research shows, that students do not appreciate that they learn better if they're active. They still think that they learn from listening in a physics course. And so at some point they start, frustration will be building in your course, not the 1st of September, but when things get tough mathematically, that why are you not teaching us? You should lecture more. We are not learning. And then you say, okay, let's figure out what we do to learn. So I'm asking you now to tell me, to think about to think about things that you love doing and do very well outside of your job. Can be, you know, I play tennis or I dance tango, you play violin, whatever you do. So I'm going to record it on slide 113. So can you tell me what you are, what your hobbies are, what you're good at other than physics and teaching? Okay, I will put tennis for myself. I'm not very
garden.
good at it, but I'm trying. Okay, anybody else?
I grow plants very well.
Okay, gardening.
Yep.
Okay. Okay. Anybody else? Come on, people.
I'm in
Drawing.
Say it again.
I said
Cooking.
drawing.
Play video games.
No, drawing.
Drawing. Okay.
Play musical instruments.
Musical instruments. Okay, good. So let's say musical instruments. Oh. Okay, who deleted cooking? Don't delete cooking. Musical
I like
instruments.
cooking, too. I like cooking.
Okay.
Cooking, soccer.
Did we have computer games? Soccer? Okay, gardening. Gardening. Okay, great. So I'm asking you, is there more than one gardening person? Raise your hand if you garden. Good, great. Raise your hands if you are in sports. If your hobby is sports, yes. Music, who plays music? Raise your hands. Okay, great. And cooking and baking, raise your hands. Perfect. So what I'm going to do now, I'm going to break you into 4 rooms and you will need to choose which room to go. I'm not going to assign you. You go into the room where you know, where you learned something, right? And what you need to do, the task is on slide 114. You need to think, how did you become good at it? Like, how did I become good in tennis? I'm not really good, but I think I am. How did I become good in tennis? What did I need to do? How did you become good in cooking? And in your group, I want you to come up with kind of a, you know, learning cycle of what you needed to do. And I'm asking you because this is what our students are. They are expert learners. They are expert skateboard, they're expert gamers, they're expert musicians, they're expert athletes. But somehow they do not bring their expertise in learning into our classes. They think that they would learn by listening to us, while in fact they know that they didn't learn anything by listening. And so in order to resolve this tension, they need to actually stop and think how they learned what they learned. And that's what we're going to do now. So I need to do the breakout rooms. I need to recreate. I need to recreate 4 rooms, but I need to, how do I make you? Oh, make you sign. I cannot change this. How do I? I am going to.
I'll do it for you.
You'll do it? Can you do it? Because
I think I can do it.
Yeah, if it's 4 rooms and they need to be able to choose the rooms.
Yes.
Because I already created them that my Zoom does not allow me to do that. Or
Do
I'm
we
not-
just choose randomly because we won't know what room is what?
Yes, let participants choose the room. Can
Yep.
you do it,
I'm
Chris?
working on it.
Okay.
The slides tell you what the 4 rooms the topic is. We have sports.
Yes, the slides tell
musicians,
you. We just
gardening,
need
and
to
cooking.
create the rooms for you to go.
Right. So if you're a gardener, room 3 is
Yeah.
where you're headed.
Right, but if the rooms are set up, you can't move. So
Hey.
join a
No.
breakout.
They are now ready. You should be
Yeah.
able to join one of 4 rooms.
Yeah. Okay.
work?
Just go. So room 1 is sports, 2 is music, 3 is gardening, and 4 is cooking. Go for it.
So you
Okay, well, you can look at all the slides and you understand you will give more than 5 minutes to your students to do that, maybe 15 minutes. But are you getting the purpose of the activity? Of the game? It's not an activity, it's a game, right? It's a game, developing an expertise game. So if you look at all the slides that were created and the gardening people, they're making a whole cycle. We just let them do it. You will see again and again the same things that repeat, right? Observing somebody else do it, trying yourself, getting feedback, failing, making mistakes, crying. You have this crying for the plants people. Cry a little and then do it again. And nobody wrote, I listened to lectures. Right? So that's not how you learn what you learned. So that's exactly what we're doing. We are letting you observe experts. We let you try yourself, fail, receive feedback. We also wrote that sometimes you need to break your task into smaller tasks. That's what we do when we first draw a diagram and then we write the mathematics. So everything that you put on the slides, we do when you learn physics. That's why if you feel stressed, if you feel frustrated, remember the thing that you're expert in learning and compare your state here, frustration with a physics problem, with the frustration that you have playing a violin or trying to go to the next level in the computer game. Would you quit if you cannot get to the next level on the first try? Of course not. So you should not quit today. So that's my speech. I saw that somebody posted in the chat, I would not do this activity as the opening week because the students do not have the need to know. They do not know that they will be frustrated. You don't need to preempt it. Do not play it on the first day. We have activities for the first day in the Active Learning Guide, Chapter 1, in the textbook. Do not play this activity on the first day. Play it only when you start getting complaints, because complaints create the need to know. Remember, in traditional education, we give students answers to the questions they don't have. That's why they don't remember the answers. If you're not buying a house and I'll tell you about mortgages, you would not remember a word. But if you are buying a house and I tell you about different mortgage rates with different banks, you will listen and remember. So creating the need to know is the crucial part in learning, which we forget or neglect or do not pay attention to. That's why do not play this game. Okay, we are getting close to the end, but we have stuff here. So summary of the expertise activity is on slide 119, there is a TED Talk, and there is a talk about growth mindset. Your students need to watch these talks, but not before they play the activity, not before they get frustrated. Do not let them do it while they don't have the need to know. Okay, working in groups, there's really great papers and studies. So if you have interest in setting up your group work better, this is what to study, not today's workshop. Slide 121 is a video of students talking about learning through IEL. You can watch it in your own time. Slide 122. This is the most important slide, I think. So in order to see all the resources, go to the website ielphysics.net. There are resources related to the textbook and then free. Most of our resources are free. The only thing that is not free for the students is the textbook. But Pearson sets up very easy online access, and they have different cheapy packages. It's really now not expensive at all. The free textbooks moved the publishers into much cheaper choices. When you got the textbook, right, from Ron O'Hara. One thing that is important if you want to use it is to start reading it as if you have never studied physics. you have to interrogate every sentence yourself. Because if you look at the section and see it's acceleration, I know what acceleration is. You don't know how we treat it. And the treatment of things, not only forces is different, but energy is dramatically different. We have a systems approach to everything. We have so many different things that will be new to you, that if you think that you know this content, which you do know, but you don't know it our way. Our way is based on research in physics education that has been done in the last 30 years, and our own. People who are co-authors of this book are active researchers, and the active learning guide and the instructor guide. So what you find there is the result of the best research-based practices. Okay? So I put into the folder, in the participant folder, chapters for the active learning guide and online active learning guide. If you want to see introductory activities on the first day of class, you see them in chapter 1. And then it just goes through kinematics, dynamics, like a regular thing. I also put the folder with the papers. If you want to read research, you're welcome to do it. Most importantly is that you join our Facebook group. Several people here are the members, and they know how the group works. We have workshops every month for different topics. We are now doing gases and thermodynamics. We started in September with kinematics. So if you are going to use our materials, which I strongly encourage you to do, then starting September, you will receive actually August, the workshop on the first day of class, then the workshop on kinematics and linear dynamics and so on and so forth. Right, Roberta and Andrew? So yes, okay. Questions?
I have a question. My concern is the same as I have for modeling physics, which is given pushes from the state, how do we get around the need to accomplish so much when teaching like this takes so much longer?
Right. So in any test, the students do not need to answer every single question. If they know how to answer well, 75 or 80% of the questions, they will win on the test. So this testing is not an argument for coverage. However, if you really want to not to cover, but let students learn all of the materials, then you use the technique that we discussed before. Some of the stuff you do in class, but after the first 4 or 5 months, the students are mature enough that you can assign them the work with the textbook on their own, because the textbook is written in this way. First, it's written with the language that they can understand. Secondly, it takes them through the same, you read chapters 2 and 3, you saw observational experiment tables, testing experiment tables, you saw the math discussions, everything. But the students can only benefit from them if they know how to interrogate the text. Teach them to interrogate the text, create their understanding of how physics works, and then you can assign some stuff for their independent work. But I wouldn't even do that. I would just say, my students know how to do well 75% of the material. If they do it on the test, they will be great. If I zoom through everything lecturing, they won't know anything. They'll do poorly anyway. So what difference does it make? Yes, Kanika.
Yeah, so I just have a question regarding the material. Like, how long will we have the access to the online book? That
as a teacher, you have access as an instructor forever. So this might expire, but then you're entitled to a free book. Okay, so there's not a matter of access. Everybody who is an instructor is entitled to a copy of a free book to decide whether they want to use it.
Okay, yeah,
Okay,
gotcha. Thanks.
we're working now in the 3rd edition. So if you start using the second, it would probably be a year and a half till it comes out. But if you're using the 2nd edition, no numbers will change. We're only adding stuff. We're not changing the problem numbers or the section numbers. So everything that you develop will stay. That's the goal of the revision. But we now have amazing problems. The problems that we're making are super amazing. And the videos and the experiments. So the book and the active learning guide and stuff will get better, but you will not need to redesign anything. Any other questions other than coverage? And
How can we access this information once we're off this chat? Are we gonna have a copy of the video that you made
what?
today, or
Of
how do we get
today?
back into the folders so that we
Oh,
can,
the folders, you have the links. You just bookmark them, the folders will stay. They're for you forever.
for the PowerPoint?
Yes, for the slides, for the links, they're all there. I'm not going to delete them.
Thank you.
You can also, Bob, download it on your computer. If you
Okay.
are afraid that you will forget the link, just download it. It will download as a PDF with all the, as a PowerPoint with all the links. So it's not a problem.
Okay, thank you.
And Larry said that the recording will be available too. Yes, Theo.
Oh, these videos that are designated like OALG_5_1 and so on. Are those with the e-textbook?
No, they're
No?
in the online active learning guide. You have access to the chapters that we use today in the folder, but they're all free on Mastering Physics. So you're set up with the Mastering Physics access now. And if you're not, ask your Pearson rep, everything is free there. And you just go and download and use them with your students. You don't need to use the textbook to use OLG or ALG.
So I mean, so right now I'm using Night with Pearson. So if I wanted to access these videos, I would switch to your textbook and then I would have access. No?
No, you just need to go to instructor resources. You don't need to switch, but I encourage you to.
And do you have a calculus-based text or just the algebra-based?
We have only the algebra. We are working on the calculus-based supplement, but I don't know when it will come out. My experience is that in the calculus-based, you don't do much calculus anyway. So you can supplement it yourself, but the problems and the flow that we have develops students so well that a little bit of derivatives and integrals is not difficult to add.
Great. Thank you so much. It's a wonderful workshop.
Oh, thank you. Thank you. Yes, Andy.
Yeah, I agree. It was a wonderful workshop, and I can see a revolution spreading out from my school now as I adopt it. So I was wondering if there was if it was viable to have a physical textbook, or is that just not a thing?
Absolutely. Absolutely. The physical textbook is available. It's printed. It's just for you to get the book for the workshop is impossible, being you in UK or people far away. That's why you got the digital access. But the studies show that students prefer to have an ebook. But yes, we have a hard copy. I use a hard copy. I never access the ebook.
Where would I order that from?
Well, you can send me, you can order it on Amazon if it delivers to you. It will deliver. But I don't think, and you probably have the division of Pearson in UK, international, they will do it. I hesitate to ask people in US to ship you the book for free, but the UK people will do it. If you need access to UK people, send me an email.
I ordered the,
sorry,
I ordered the version that's available loose leaf through Mastering Physics, and I should have it in a day or two. You might could do that.
Thank you.
Yeah.
I've just signed up to the. So I'm gesturing at you there, my big finger. I've just signed up to the Facebook group, and I needed to put in a thing to get you to agree. How quickly do we get onto the group and start seeing posts?
As soon as I finish the workshop and admit you.
You're going to have hundreds of new members. Okay,
I am the
thank you very much.
manager. You are not going to get admitted this minute. But in order to get in, you need to say, I was in the workshop or something, so I know it's you. Because I don't remember all your names. And there's a question there. You need to answer the question. So just say, Eugenia, I just attended the workshop. That will be enough for me. I do not let anyone in who did not answer the question in detail, but not for you.
I called it a seminar. Don't let that put you off.
Okay. Okay. So I would like you to write on slide 123 what you learned in this workshop. We're a minute past, so I hesitate to do it. But I would like you to say or to write what you learned. What is one thing that you would take away?
And I will stop the recording now.
Yeah.
Thank you, everyone.